3D printing is an additive manufacturing process. It's a versatile but very slow manufacturing technology compared to high-volume production processes like injection molding. 3D printing is fundamental to rapid prototyping and design verification. The most prevalent type of 3D printing is fused deposition modeling. FDM 3D printing is the process of extruding molten plastic to build a 3D model layer by layer. From idea to physical part, this process is comprised of three fundamental steps: creating a 3D model, slicing it, and finally printing it. The slicer software converts a 3D model into layers and reproduces the model as G-code, which are X, Y, and Z coordinate instructions telling a machine to move the extruder, building the model layer by layer. The most common FDM material is PLA and ABS plastic. This process material is referred to as a spool of filament. The filament is fed into the printer's hot end. The hot end is the business end of a 3D printer. The hot end is comprised of the extruder nozzle and heater. Here, the plastic is heated and forced through a small nozzle. The hot end extrudes plastic onto the build plate. Your success in 3D printing will rely not just on your ability to design in CAD, but your ability to design for the manufacturing method of 3D printing. Most designs are suitable for 3D printing, but not all will be a success. There are fundamental design principles associated with preparing a 3D model for printing. We'll cover the fundamental characteristics like orientation, overhang, shrinkage, and supports as we look at some practical examples. Later, we'll explore some intermediate topics like print quality, infill, and build plate adhesion. TechSpark offers a variety of 3D printing machines and technologies. These machines range from industrial R&D grade machines with 2 filaments, including support and main material, like the Stratasys F170 and Dimensional Elite machines, to more user-friendly consumer grade machines like the Dremel 3D40, and other technologies like SLA, like the Form 2 machine. From here on, we're going to focus on the Dremel 3D40. This machine is self-serve and TechSpark and is available free to use whenever you have a model ready to print. The Dremel 3D40 uses a variation of Cura called Dremel DigiLab. Cura is an open source 3D printer slicer software. Many open source and consumer level 3D printer manufacturers support Cura. And thanks to Cura, most 3D printing slicer softwares have adopted a somewhat standardized layout. Just note, Cura is free to download and install on your personal computer, as well as any derivative of it like Dremel DigiLab. We're going to be using DigiLab since TechSpark has many of these machines. Just note, this is a variation of Cura. The same principles shown here apply to the vast majority of 3D printers and their respective Cura-based slicers. If you use any other consumer-grade 3D printer, and there's hundreds of these, you'll likely use Cura or some variation of it. What you're going to learn here translates to any Cura-based software, just with a different coat of paint. First, we'll look at how to take a 3D model we created and save it as a universally compatible 3D print file like .stl or .3mf. Both are widely accepted formats. If you have created a model in SOLIDWORKS, simply click File, Save As, and select .stl or .3mf from the drop-down menu. Confirm you want all mesh geometry to export to STL, and that's it. Multi-part assemblies can be saved as STL or 3MF formats also. Just note, any gaps between your geometry or unusual inconsistencies between meshes may produce errors in certain slicer softwares, or they might just simply crash it. When saving a multi-part assembly as an STL or 3MF, make sure the system option Save All Components of an Assembly into a Single File is selected. For multi-part assemblies, this is usually the case. With a basic STL or 3MF file, we'll move on to the slicer software Cura, or Dremel DigiLab in this case. To start, we will import a 3D model that we wish to print. You can move the model around the build plate. This might be necessary for large models where position affects printability, but printing in the default location is usually sufficient. If printing duplicate parts, do this by right-clicking on your model. Arranging your models with the Move command may be necessary. Note, for low-end consumer-grade printers, there's a higher chance of success when printing a single part at a time. You can also scale your model within the slicer. When using .stl files deriving from various CAD programs, the slicer software may not be able to recognize the associated units of the model, like inches versus millimeters. You can scale your model to quickly fix this problem. This issue typically does not occur with .3mf files. The STL format has been around for over 30 years, hence its apparent high popularity and wide adoption. .3mf is relatively new compared to STL, but vastly superior to STL. 3mf delivers complete model information into a single archive. Regardless of the file format you pick, note that most fused deposition model-based prints will shrink. Your model is printed with hot filament or plastic here. Once cooled, said plastic will shrink. On average, parts typically shrink by 1% when using PLA-based filament. This amount will vary based on the overall size of your part, its orientation, and again, material that you're using to print. You'll find when printing screw holes, mounting brackets, or mating parts, they might not fit as you dimensioned or toleranced. Depending on your CAD design, you can simply scale your model here to compensate for shrinkage. Scaling can be done uniformly, so the same ratio across the X, Y, and Z axes, or just along a selected axis or two where the shrinkage is more prevalent. Knowing this and exercising good design principles will alleviate this one downside to 3D printing. In general, a good design principle is knowing what manufacturing technology you're going to use to create your part. With 3D printing, it's good to have relaxed tolerances where applicable, or, for example, using slots instead of holes when you're mating two parts. Orientation is one of the most important aspects of 3D printing. Orientation determines the strength of your printed part along with the overall probability of a successful print. The most basic use of this tool is to orient your part in the best interest of a 3D printer's capabilities or its limitations like bed size. Some printers have rectangular beds, so longer parts may need to be rotated in the slicer so they fit within the print volume. Clicking and holding one of the axis rings will rotate your part along the X, Y, and Z axes. The rotations are usually increments of 15 degrees. When rotating your part, you might have difficulty selecting the correct face that you want laying flat on the print bed. Sometimes it's easier to identify the bottom of your part and have the slicer place that face against the build plate. Clicking Select Face to Align to Build Plate does this. This feature is found in the base version of Cura. Dremel DigiLab does not have this feature in the current version at the time of this video. However, rotating your part and then using lay flat will also accomplish this task. Tall, thin part is best suited printed laying down with more contact touching the build plate. Proper part orientation can also influence the overall print time, but this usually isn't a deciding factor unless you're trying something ridiculous. Aside from a reduced print time compared to standing up, mindful orientation also improves the probability your print will be successful. However, there is more about orientation than just what's best for the printer. We also have to consider what's best for your part, like strength. Remember, your part is built layer by layer. Each layer is a lamination of extruded filament on top of the previous layer. The weakest part of the structure is the bond between each lamination. A continuous extrusion of filament is relatively strong compared to the bonding strength between each extruded layer. For example, this 3D printed ring can be used to hang stuff or hold a load and tension. The strength of this ring is inherent to its internal structure or how it was printed based on its orientation to the build platform, meaning the orientation affects the part's overall integrity. To simplify this example, both variations of this part will be hollow. Which one of these examples is stronger, the ring laying flat against the bed or standing up? To find out, let's switch to the preview mode, or sometimes called the view layer mode. This showcases not only the overall fidelity of the print, but also the fundamental structure the print will take. When in preview mode, we can use the slider bar to move between each layer of the print, giving a good view of the cross-section at any layer of our part. Just note, if you want to manipulate your part, you have to switch back from preview mode to prepare mode, or sometimes called solid mode. So which one is stronger? If you guess the ring laying flat on the build plate is stronger under tension, you are correct. But why? Looking at the cross-section of each orientation shows how the part is built. On the right, pulling this ring will result in a break between the printed layers. This principle is the same when you split wood along the grain. The orientation of the left takes advantage of a continuous extrusion of filament. Pulling the ring here results in a more resilient part, because the load is spread over a continuous strand of extruded plastic. This example is an oversimplification, but the principles still apply if you design and print a part that continues to break under mechanical stresses. If your 3D printed part is load-bearing or will experience strenuous forces, orientation will make or break the performance of your part in the field. There are other ways to improve a part's strength beyond this. We will explore one feature later, but just know 3D printing does have its limitations. Orientation also affects support structure. You cannot overcome gravity when printing. You cannot print without a previous layer underneath. Of course, there are exceptions, and this is referred to a part's overhang. A modest amount of overhang can be printed without support, and this is usually limited to about 45 degrees. Slower printing is better for parts with lots of overhang. Features that exhibit overhang are usually marked in red by the slicer. Adjusting a part's orientation can help minimize the need for support structures, but sometimes supports are inevitable. Support structure is a sparse density filler that breaks off easily from your model. We'll talk more about overhang and supports in a bit and some advanced features. Mirror is a helpful tool and is the last basic tool that we'll cover. Mirror is useful if you have a two-part design like a hinge that can be mirrored to produce its complement. You can mirror the part and or create the duplicate in the slicer. There's no need to do this in CAD. Next, it's time to discuss some more advanced attributes to 3D printing. These being print quality, infill, supports, and build plate adhesion. Again, these attributes are trade-offs in the grand scheme of things. You can't have it all. That being a highly detailed part in the shortest amount of time. If you want a finely detailed part, it'll take longer to print compared to a part with minimal detail. If you want a stronger part, it will cost you more in filament resources, become heavier, and again, may take longer to print. Just a general reminder, the more you deviate from recommended settings, the further away you may deviate from a successful print. Let's focus on our first trait, print quality. This is a general term that covers two main characteristics, layer height and print speed. Both are directly related to each other. This can be best seen by the estimated print time when slicing your part. Low quality settings are always faster compared to high quality settings. The difference here is how many layers your model is sliced into. High quality or high detail slices your parts into more layers, each layer being thinner compared to a low quality slice. Most of the time, manufacturers have already determined the ideal print speed a machine can move while still producing quality extrusions. If you want to make your print faster, your main trade-off is to reduce the part's layer height. Layer height is print quality. This also directly affects the level of detail or fidelity you'll see in your model. A finer resolution or small layer height can reproduce finer details at the cost of total printing time. A coarser resolution or thicker layer height is a faster print at the sacrifice of part detail. The more layers, the longer the print and the more detailed the print will become. Most consumer grade printers use an extruder with a nozzle diameter of 0.4 millimeters. Not all, but most. Low quality or fast prints have a layer height closer to this nozzle diameter, but never exceeding it. High resolution prints have a layer height a fraction of this diameter. The actual print speed, or in literal terms, the speed the printer is laying down filament, is typically held constant between changing layer heights or print quality settings. Changing the print speed to a value faster than the recommended setting has a cascading effect on almost every variable related to a successful print. Changing the print speed is not recommended for beginners. Adjust your layer height or slice thickness if you need a faster print. The slicer preview or layer mode is a good way to illustrate this point between print qualities. Just note, the more you deviate from recommended settings, the further away you may deviate from a successful print. The next significant influence on your part is the part's infill. This is the part's internal density. Typically, we start at 20% infill and work our way up based on needs. The more infill, the longer the part takes to print and the more material that's consumed. Infill is the density across the entire part. Generally, a greater infill will improve the overall strength characteristics of your part. However, this benefit will start to plateau around 75% infill and up. Infill patterns are automatically generated by the slicer, though some slicers give you other options here. Cura, for example, has a wide variety of infill patterns left best for you to experiment with. However, the default infill pattern will typically work for most parts. Experiment with different infill percentages. The higher the infill, the more material is consumed to build your part. Remember, using more filament inherently drives up the cost of your part. A 100% infill for a part that is still at the proof of concept phase is not a good use of resources. Another downside with higher infill percentages is more material means a longer print. Infill does have a significant influence on a part's strength, but with limitations. Remember, we can never exceed the strength properties of the filament. A mindful infill coupled with thoughtful part orientation are the best assets for strong parts. Depending on the geometry, printing a part with 0% infill doesn't usually generate great results. We can print our ring with 0% infill because the exterior geometry stays around the 45-degree overhang rules or 45-degree draft angles. However, this cube does not. The last few layers that make up the top of the cube will fail without support structure or infill underneath. What if you need a really strong part but have exhausted the limits of good part orientation and reached optimal infill? What else can be done? You can also change some features that influence how the interior of the part is built beyond the infill pattern set by the slicer. These two rings have the exact same layer height and 100% infill settings. However, the one on the right was set to an exceedingly high wall layer count. This forces the slicer to lay continuous strands inside the part following the profile pattern of the part's shell. An exceedingly high wall layer count can override infill patterns. So now between the two, which ring do you think is stronger now? Okay, so this example is an oversimplification. Its purpose is to emphasize the flexibility the slicer allows if you know what options to seek. Remember, strength based on infill alone will plateau around 75% infill and up. You won't see much change in strength in a part with a 75% infill other than it costs more to print. To get the best of both worlds, that being a strong part while using the least amount of material, you'll have to experiment with increasing the thickness of your part's shell along with infill. There's a magic ratio between both that will give you economical strength, assuming your part is sufficiently designed in the first place. Yet another option is adjusting the wall shell count, and that can also help you discover that magic ratio to strength and part density. So part density now being the infill along with the shell count. Lastly, and this is more for the wow factor at the novice level, these are infill patterns. Note, not all slicers will support the option for infill patterns. The effects of infill patterns are more influential based on the overall geometry of your part. Just note, some of these patterns can inflate your G-code file significantly. And on lower end printers, these complex patterns might just result in headaches rather than a successful print. All the options discussed here, which were infill, shell wall count, and infill patterns, will yield the best results if you experiment with them and have patience. There will come a time when you need to have the slicer generate support structure to build your part. This is very common. Fortunately, this feature is automatic as long as you have the feature called supports turned on. Overhangs that exceed 45 degrees or elevated features above the build plate need support. Overhanging features are usually identified by a red colored face on the surface of your part. Supports are usually easy to remove as long as you have access to remove them. If they're buried inside your part, you will not be able to remove them easily. The more support your part has, the more post-processing of your part might be required, essentially cleanup time. Remember, any area where support's attached to your part may leave a blemish. Thoughtful orientation is a good way to counter the need for supports. However, supports are a helpful aid when printing complex parts. Sometimes supports are necessary, and your part will be better with the inclusion of supports. Build plate adhesion is one of the more overlooked features when it comes to troubleshooting a print. Simply, build plate adhesion is the method and the amount of material and surface area connecting your part to the printer's build plate. Your print has to remain still when printing. Keeping it stuck to the build plate is the only way to do this. The most common failure in 3D printing is the print failing to stick or remain stuck to the build plate. Some printers mitigate this by using a heated build plate. There are a few options for build plate adhesion. Let's look at a few under the build plate adhesion option. None is what it sounds like. Your model and nothing else, that's all that's being printed. Skirt is always recommended. This does not provide any extra surface area to aid in your part adhering to the build plate. However, it does prime the nozzle before attempting the first layer of your part. The skirt simply forces the printer to extrude some filament. This is akin to priming the extruder. The skirt ensures filament is present before your model starts printing. When the nozzle heats up prior to a print, sometimes gravity can pull filament out of the hot end, creating a void of filament. If you start your model with this absence of filament, your first layer will contain inconsistencies or worse, fail to stick. Watching the skirt layer print is also a good identifier of your printer's basic configurations. Some telltale signs of extruder blockage, unlevel bed, or nozzle height problems are shown in the skirt layer. Brim. Brim expands the silhouette of whatever is touching the build plate, creating a larger surface area for your print to stick. The brim is always printed with concentric extrusion rings, making the brim layer peel off from your part with ease. Parts with relatively small surface area in contact with the build plate will benefit from using the brim. Large parts with corners that are susceptible to lifting or warping from the build plate can benefit from using brim also. Raft. Raft is not a typical use case, except in the presence of ABS filament. This is more common in industrial R&D type printers that primarily use ABS filament. Raft builds a platform made from filament. Your part is printed on top of this platform. ABS can be a stubborn material to print with, and a raft aids with the build plate adhesion and reduces the chance of that part warping. Among these 4 build plate adhesion options, which are best suited for typical day-to-day 3D printing? Well, raft is a special use case, usually only for special materials like ABS or filaments known for being difficult to stick to build plates. That leaves us with 3 options. If you rank them in order from usefulness, they would order as follows. None being the least useful, followed by skirt and then brim. Brim is the best of both worlds, which primes the nozzle similar to skirt, but also serves double duty by providing extra surface area for build plate adhesion. When in doubt, always use brim as your go-to option for build plate adhesion. You now have enough exposure to be successful with 3D printing, in particular using 3D printing slicing software. In summary, we talked first about the basics: orientation, overhang, scale, and supports. Then we went into more advanced topics like print quality, infill, and build plate adhesion. This video condensed a lot of topics that might take time to grasp, but don't be afraid to revisit a topic again, and above all, experiment with the slicer software. Remember, design your model for the manufacturing process. 3D printing in this example is an extremely versatile manufacturing process, but it has its limitations too. With so many variables to adjust, it's possible to branch off into a path that always produces good results, and then on a different machine or one more tweak produces failed parts. Sometimes a combination of refining your CAD design and experimenting with the slicer will yield optimal results. Never be discouraged if your first part doesn't turn out right. Rapid prototyping involves experimentation. Learning from those mistakes is experience.